Hi, and welcome to my presentation on the engineering failures of the Titan submersible. In June of 2023, the Titan submersible was lost during a commercial dive to the wreck of the Titanic. The vehicle experienced a catastrophic implosion while descending to a depth of nearly 3,800 meters. From an engineering perspective, this event is significant because the Titan was a human-rated pressure vessel operating in one of the most extreme environments on Earth, the deep sea. Rather than focusing on speculation or blame, this presentation will take a look at the disaster as an engineering case study examining known design decisions, established engineering principles, and the lessons that emerged for future engineering practice. At extreme ocean depths, the primary engineering challenge is hydrostatic pressure. Pressure increases linearly with depth, and at the depth of the Titanic wreck, the external pressure is several hundred times greater than atmospheric pressure at the surface. Any submersible operating at this depth must rely on a pressure hull capable of resisting uniform external compression. If the hull loses structural integrity, failure occurs extremely rapidly. This environment leaves very little margin for error, which is why pressure vessel design is one of the most critical aspects of deep sea engineering. The Titan submersible used a pressure hull made primarily from carbon fiber composite with titanium end caps. Carbon fiber composites are widely used in aerospace and other industries because of their high strength to weight ratio. However, composites behave very differently from traditional pressure vessel materials like steel or titanium. Carbon fiber is anisotropic, meaning its strength depends on fiber orientation, and while it performs very well in tension, its behavior under sustained external compression is less predictable. Another important difference between composites and metals is how damage develops. Metals tend to deform or yield in visible ways before failure, while composite materials can accumulate internal damage without obvious external signs. In a deep sea environment, repeated dives subjected the hull to cycles of extreme compression followed by unloading. Over time, this cyclic loading can lead to micro-cracking, delamination between the layers, and a gradual loss of stiffness. These damage mechanisms are difficult to detect visually and complicate long-term structural reliability. Fatigue is a critical concept in engineering systems subjected to repeated loading. Each dive of the Titan exposed the pressure hull to a full pressure cycle, and fatigue damage is cumulative. While fatigue behavior is well understood for many metals, there is no universally accepted fatigue life model for large composite pressure vessels operating at extreme depths. This introduces uncertainty when predicting long-term structural performance. From an engineering standpoint, using a material system without a fully validated fatigue life for a human-rated application significantly increases risk. Most human-occupied submersibles are designed and tested under the oversight of independent classification societies such as the American Bureau of Shipping or the DNV. These organizations require conservative safety factors, extensive testing, and third-party review. The Titan was not certified by a major classification society. Independent verification plays a critical role in engineering safety because it helps identify failure modes that internal teams may overlook. Bypassing this process removes an important layer of risk mitigation. The Titan reportedly used acoustic monitoring systems intended to detect cracking or structural damage during operation. While monitoring systems can provide valuable information, they do not replace preventative design. Detecting damage does not prevent failure, it only indicates that failure may already be developing. In pressure vessel engineering, safety is typically achieved through conservative design margins and validated materials, not through real-time detection of damage while it is in service. Although the exact sequence of events inside the hull has not been publicly detailed, the implosion behavior is consistent with a loss of structural integrity in a pressure vessel under extreme external pressure. Once failure initiates, collapse occurs almost instantaneously due to the enormous pressure differential. This type of rapid failure leaves no opportunity for corrective action, and it highlights the unforgiving nature of deep sea environments. In response to the Titan disaster, the engineering community has reinforced several long-standing principles. These include the importance of independent certification, cautious use of experimental materials in safety critical applications, and clear distinctions between experimental prototypes and commercial passenger vehicles. The event has also renewed discussions about material validation, fatigue testing, and the role of standards in protecting human life. The Titan submersible disaster was not the result of a single isolated mistake, but rather a combination of material choices, testing philosophy, and risk tolerance. From an engineering perspective, it serves as a powerful reminder that innovation must be balanced with verification, especially in human-rated systems. The, the lessons from this event will continue to influence engineering education and safety practices moving forward. I did use AI in the completion of this assignment. I used ChatGPT to help me in the preliminary research and brainstorming phase of this assignment. I also used it to help me construct the script. I found it to be a valuable tool to help me understand certain concepts and the PowerPoint app as well. Thank you.